All right, let's get started. So this is going to be the last lecture that we're going to be talking about periodic dynamical systems, but it's also, I think up to now, the most mathematically involved lecture we're going to have. Basically, we are going to discuss a different way of computing sensitivity of statistics, like infinite time averages, with respect to parameters on the periodic system. All right, so last week, actually, we discussed that a periodic system has a zero Lyapunov exponent, meaning that if you perturb the system a little bit, initial condition a little bit, the perturbation would never, most likely, would never die down, right? It would never increase nor decrease. And this is really a subdued version of what's going to come in chaotic systems. And we see that even that has a lot of impact on the sensitivity of a perturbation in the parameter, especially how we compute them, right? So the naive way of computing them actually breaks down because the limit and the derivative, the limit of time goes to infinity, the average in time goes to infinity, does not exchange with the derivative, right? So we discussed already one way of computing that using windowing. It's the homework problem you're going to be looking at. Today we're going to discuss a different way of computing the derivative of long time averages with respect to parameters. And that way of computing starts to look at the phase space rather than looking at just the time direction. And it is this kind of thinking, mathematical thinking, that is really a prelude to what's coming in chaotic systems. So we're starting to look at densities on the attractors and how the densities are going to shift on the attractors. Okay, so this new method is called the time dilation. So what does that mean? What it means is that when we are looking at a dynamical system, du dt equal to f of u, and with a parameter s, okay? Consider two systems, one the original system and the other one slightly perturbed system with f of u, s plus an infinitesimal delta s. The two systems, as we have already seen, evolve at a slightly different clock, right? In the sense that when the black system completes a period, the red system might be slightly ahead or might be slightly behind. So these two clocks for every period would be offset by some infinitesimal amount. So as the number of periods goes on, the clocks are offset more and more and more, and eventually lead to breakdown of our algorithm for computing sensitivities if we didn't use windowing, right? So the idea of time dilation is based on the assumption, first of all, a critical assumption that whatever quantity of interest we can define, right? Let's say J bar, defined as the infinite time average of some J on U, is differentiable to the function f itself, right? So is differentiable to f of u. So what does that mean? Okay, that means if you have two perturbations. So if I have okay, so the differentiable means the derivative exists, right? And the derivative is always a linear function that maps a perturbation to the change in the objective function J bar, right? And what does a derivative to a function mean? Anybody knows like derivative to a function? So nobody studied the functional analysis, I guess. So basically, a derivative of function is basically a map from a function to, okay, so the derivative of j, delta j bar over delta f is defined as a linear map, right? A map from delta f to delta j bar. And this map is linear, right? So the key word actually is the linear. Is a linear map from delta f to delta j. So that is basically saying that what does linear mean? Linear means if you double the delta f, my delta j bar is doubled, right? If I have two delta f's, let's say delta f1, delta f2, the effect of the combined delta f1 and delta f2 would lead to a combined delta j1 and delta j2, right? So basically, the effect of delta f1, let's say in general, linearity means the effect of a delta f1 plus b delta f2 is actually a delta j bar 1 plus b times delta j bar 2. So this linearity actually would allow us to decompose the effect of a small parameter perturbation into two parts. One part only perturbs the location of the attractor, but does not change the period. Okay, the other part only changes the pace, only changes the clock, but does not change the location of the periodic limit cycle at all. So this assumption would allow us to, so the differentiability allows the decomposition of really a delta f, right? A changing f, a decomposition of, let me say delta f, which is defined as f of, so delta f of u is defined as f of u s plus delta s minus f of u, right? So that's the change in the right-hand side of the function, okay, into two parts. Okay, so let me say this is equal to delta f1 u plus delta f2 u, and then we'll be computing the effect of delta f1 u and delta f2 u independently using two methods. And the why? This is because we want to decompose this delta fu such that, okay, such that delta f1 does not change the frequency or period. Okay, and delta f2 only changes the period and does not change the shape of the attractor, which actually means delta f2 is going to be aligned with the direction of the time evolution, right? So the effect of delta f2 is just a scaling up and down of the existing f of u, right? So delta f2 is actually equal to f. So let me see, u is equal to f of u plus just scaled up by a scalar. So let's call the scalar. Let's call the scalar psi of u. So psi of u is basically a scalar that depends on where you are on the attractor, that either accelerates the time evolution if psi of u is positive, or it slows down the evolution of the trajectory if C of u is negative, right? So that's actually the psi of u. The effect of psi of u is why we call this method time dilation, right, or compression. If it's so basically that means if psi of u is negative, right, the effect of the delta f2 term is dilating time, is making time slower than what it was originally. If psi of u is positive, it accelerates time, it compresses time. Right? Any questions of what we are doing?
If it's, the psi is positive, it means...
So if psi of u is positive, then if you look at the effect of delta f2, right? So then basically if you add a delta f2 term on the right hand side of the equation, right, it means the right hand side is exactly the same vector but a little bit longer, right? So basically we are du dt would be into the same direction but faster.
Faster, so it increases the amount of error?
Faster means so for example, if C of u is positive along the whole trajectory, right, that means my period is going to be reduced, my frequency is going to be increased, right? So let me give an example, right? So if I have a let me just give my example, okay, dx dt equal to 1, where again x is going to be in r mod z, right? So basically in the periodic domain from 0 to 1. Okay, so if I introduce delta f2, that is I scale up, right? So if I scale up, then my dx dt would be perturbed into 1 plus c of x, right? So basically, if c of x is positive, then dx dt would be just bigger, right? I'm going between 0 and 1 faster. If dx dt is negative, that means I'm slowing down. And particularly, the c can actually depend on x, right? It can be sometimes positive, sometimes negative. That means I'm going to be spending more time where c is negative. I'm going to be spending less time wherever c is positive.
So the assumption we made that this map is linear, it's just assumption, right?
Yes,
and
right.
How much does it close to reality?
How much is that close to reality? Actually, more than we think. So it turns out that for periodic systems, right? So for example, let me actually give this as an example, right? So this is a very simple periodic system, right? So if you have a fixed point, if you don't have a periodic cycle, if you just have a fixed point, the fact that then J bar would be actually equal to the objective function at that fixed point, right? Okay, and in order for J bar to be differentiable to the right-hand side of the system, we actually normally require two things. One is df du is full rank, right? So that when you perturb f a little bit, right, the fixed point wouldn't be perturbed to by an infinite amount. So that's usually requirement number 1. And requirement number 2 is that my objective function j is differentiable in the phase space, right? So when the fixed point is perturbed by a little bit, my j is also perturbed by a little bit, because my j bar is actually equal to j at that fixed point, right? So 2 requirements. One is really the well-conditionedness of f, and 2 is the differentiability of j. And when we get to a periodic system, right, we actually see that it still poses some good requirements on f, but it no longer actually strictly requires the j to be differentiable. Interesting, right? So for example, in this system, my j can be either 0 or 1 depending on where x is. If x is between 0 and 0.5 and between 0.5 and should say 1, right? If in this case j is not differentiable, but you can actually show that j is actually differentiable to the form of the right-hand side. I mean, j bar is differentiable to the form of the right-hand side, because when you smoothly perturb the right-hand side, you are accelerating or decelerating the system, and you are making the system spending more or less time in the left half or the right half of the periodic domain, right? And thus you can show any tiny perturbation to the right-hand side actually would only produce a tiny perturbation to j bar. Like any tiny perturbation on the right-hand side is going to only slightly increase or decrease the fraction of time the system spends on left or right of the side of the domain. So we are going to see that when we derive the formula for computing the sensitivity due to a time dilation, which is due to the delta F2 term, right? It actually does not contain any derivative of j with respect to the phase space, right? So we only need the value of j, we don't need the derivative of j. And as a result, even a discontinuous but otherwise integrable j is actually going to give you a finite sensitivity. Okay, but on the other hand, especially for some chaotic systems, the differentiability is actually not true anymore. And it turns out that even figuring out computationally whether a j bar is differentiable on the particular system actually requires a lot of computational effort. And this is actually something we are going to discuss in the chaotic section, right? Is to how do we determine if a system would produce differentiable statistics or not? Because it's actually remarkably easy to find systems that does not produce differentiable statistics in chaotic systems. All right, but for periodic systems, it is usually the case that the j bar is differentiable. All right. Okay, any other questions? Okay, so what we have done is we decomposed any changing f due to a changing parameter into two parts. One part does not change the period, and the second part does not change the location of the attractor, right? So this is actually generalizable even to chaotic systems. We can always decompose a change into two parts. One part does not change. One part does not change. Does not change the period. Yes. So one part only changes the location of the attractor, right? But has a minimum or fixed or easily computable effect on the distribution of the density on the attractor. And a second term would not change the location of the attractor at all, but shifts the density, the distribution of the stationary measure on the attractor. So this is something we'll start to look at using periodic systems because it's much easier to conceptualize and visualize in this case. And so for example, what does it mean by shifting the stationary, shifting the density on the attractor? It simply means that it increases or decreases the amount of time, the average amount of time, the fraction of time a infinitely long trajectory spent on any particular portion of the phase space, right? So that's shifting the density. Okay, so this is conceptually how we are decomposing the delta F, but computationally, how do we do that? Well, computationally, it is easy to understanding what the second part means, right? The second part means I want a perturbation that's aligned with the direction of the time evolution. We know what f of u is, right? And therefore, we know we can enforce the second requirement. But how do we enforce the first requirement? That's
we find the second one, we can find the first one.
Yeah, after we find the second one, we can find the first one, but that's actually pretty much what we are going to do. Okay, so let me define what we are going to be doing. Okay, so the time dilation essentially solves the linearized equation. We are solving the linearized equation d v dt equal to partial f partial u, right? That's a matrix times v plus partial f partial s. So that's the linear equation that is forced by this. This is really delta f. Let me just call it delta f. So this is a partial f partial s times delta s, right? So that's delta f. Okay, we are going to actually decompose this delta f into two parts, in the sum of the two parts, right? So basically the solution to this equation is going to be decomposed into two parts. dv1 dt has to be equal to df du times v1 plus delta f1, and dv2 dt is going to be equal to delta this times v2 plus delta f2, right? Where delta f has to be equal to delta f1 plus delta f2. So as we know that the delta f2 is actually equal to a scalar times f itself, right? F times chi, a scalar, right? So that's a function of u. So delta f1 therefore can be written as v1 plus the delta f minus f times chi of u, right? That's just using the fact that delta f is equal to delta f1 plus delta f2. And we are going to enforce a very particular constraint on the solution v1. We are going to force v1 dot with f to be exactly equal to 0. Okay, so what does that mean? That means the perturbation cannot contain any direction, cannot contain any component that is tangential to the limit cycle at all. The perturbation has always have to be orthogonal to the trajectory itself. And basically this additional term is actually going to be chi is going to be, if you just look at the combination of these two equations, right? Delta f is well defined, is already, it's really provided by the form of where delta f is equal to df ds times delta s, right? So that's given by the system itself. And we are introducing another scalar variable, chi of u, right? Which is a function of t that we don't know yet. But we are also introducing another scalar equation at every time t. So we are essentially converting this differential equation into a differential algebraic equation, right? With this chi u serving like a Lagrange multiplier. Okay, so that's basically what we are doing here. So the system, without even considering the second equation at all, can be solved numerically, and then the result chi can be plugged into the second equation if we want to solve it, right? And in particular, the first equation, because of this orthogonality constraint, as time goes on, the solution would never increase, right? Because we have already seen that if the solution to the tangent equation has a linear increasing component, that linearly increasing component is going to be aligned with the time evolution direction. And if the solution is orthogonal to the time evolution direction, it will not increase.
V1 times f, it's like a normal to the trajectory.
Yes, V1 dot with f, right? This is the dot product.
There is no growth in other way than normal to that direction, right? Only changes will be tangent to the trajectory.
Yes, the increasing component is tangent to the trajectory, right? So if you solve this middle equation, the middle equation will most likely have a linearly increasing solution, right? But if you solve the first equation with the third equation as a constraint, it will not have a linearly increasing solution.
Yeah, so but it changes the period then.
It does change the period, exactly. So the changing period is going to be captured by the second component, is going to be captured by the effect of delta F2.
But in the condition we mentioned, delta F doesn't change the period. So is it?
So delta F1 does not change the period.
Means that
Delta F2 will mostly likely change the period, yes.
yeah, but V1, the constraint we defined for the V1 times F, it means that it changes the period, right?
Sorry, can you, V1 dot F is equal to 0?
It means that all growth will be in the direction of trajectory.
So V1 dot F equal to 0, what does it mean? So V1 is the result, so V1 is the difference between two solutions. One solution has a right-hand side equal to f of u. The second solution has a right-hand side equal to f of u plus delta f1. Right, so V1 represents the difference between these two solutions. Now, what it means is that as time evolves, the two solutions would be different, right? The difference between these two solutions will always be orthogonal to the evolution of the trajectory. So maybe let me draw an example. So this is the solution. Let me say this is the solution driven by f. And let me say maybe this is the solution driven by f plus delta f1, right? Okay, so what it means is that the difference between, this is V1 at t, this is this is u of t, and this is u of t plus V1 of t, right? So that's the second equation. So what this constraint means is that V1, which is the difference between the red point and the black point, is always orthogonal to the black line, right? So f is this vector is f, right? F dot with V1 equal to 0 means the green vector is V1, right? Black is orthogonal to green. So as time evolves, right, as time goes on, these 2 points, the red and black points, evolve together because their difference always has to be orthogonal to the black line. This actually prevents the two systems to have different periods, right? Because they are always synchronized. All right, make sense? Okay, so as we said, this is a differential algebraic system. So it sounds like it's going to be more difficult to solve, right? But in reality, there is a very easy solution to this problem. And the reason is because these both are linear equations. So the first equation is a linear equation, and the constraint is also a linear constraint. So what we can do actually is to really just find, first of all, we can solve this equation without this additional what we call time dilation term, and then project the solution V into the direction that's orthogonal to the time evolution direction F. So we are going to see why the projected solution actually satisfy this equation. Okay, so basically solution method we don't need to know no need for the differential algebraic equation solution. Okay, so basically we're going to say V1 is actually equal to V minus what? Minus V dot F divided by just the norm L2 norm of F. So that's basically projecting the component along F out of V. So why is that the case? You can see that's the case simply by substituting V1 into this equation. Okay, if you substitute V1 into this equation, what you're going to see is that df du times V1 would be just equal to df du times V minus df du times this. Now, what is this? This is a scalar. We have to multiply by f. This is do we need a square? I think we need a square, right? Yeah, need a square on the denominator. So this is really the projection of v out of the direction of f. Okay, so this is a scalar. Okay, so df du times the second term is just equal to this, the same scalar, times df du times f. What is df du times f? What? Yes, df du times f, yes. Right, so df du times f, as we remember, like we have said that f by itself, right, is actually a solution to the linearized equation, right? So essentially, so d dt of this is actually just equal to df is equal to df du times v plus delta f, right, minus okay, so there are two terms, right? One is d dt of that scalar, of that time dilation term, times f, and the second is minus that scalar. I think I have a square. That scalar times df dt, right? So, and what is what is df dt? Df dt is actually equal to just the right hand side, the df du times f, right? So this is df dt. Yeah, this is because f is actually du dt, right? And df du times du dt by chain rule is df dt. Okay. So right. Yeah, so what we have seen is that by combining this term and this term, what we get is this is actually equal to df du. remember the first parenthesis is a scalar, right? V minus V dot F, the square F, right? This is just combining these two terms. So so this is the same as this. And then we have plus delta F minus d dt of the scalar, right? F square F, right? Okay, so this is actually exactly what the first equation is, right? So basically, it is the left-hand side is dv1 dt, right? This is the derivative of v1. The right-hand side is df du times v1 plus delta f and minus this delta f2, which is exactly aligned with the time evolution direction f. It also, this derivation not only proves that we can compute v1 by projecting v out of the direction of the time evolution direction, it also tells us what this chi of u is. It is simply the time derivative of how much we need to project out of this direction that's aligned with f. All right. Any questions so far?
For the solution method, how we know that v1 equals to v minus something?
So this is basically a proof that if v1 is equal to v minus the projection of v in the f direction, then this v1 satisfies the first equation and the third equation, right? I mean, v1 satisfies third equation is by construction, right? We are actually explicitly setting the direction in the f direction to be 0. And it also so what we have done is we have derived that this v1 also satisfies the first equation with a chi of u equal to that guy. All right.
It's a proof, but we assume that to get to that point, right?
Basically, we have shown that if v1 is equal to this, then v1 satisfies these two equations, right? And because these two equations are well defined, it's a differential algebraic equation with one additional Lagrange multiplier and one additional constraint. The solution is unique, right? Under certain well defined conditions.
I mean, is there any way that analytically, mathematically define that v1 equals to something? Or it's just...
Yeah, I think that's what we have done, right? So to show something is true, you can mathematically you can say that the solution is unique, right? And then you construct something that satisfies the solution, then this thing you constructed is going to be that unique solution.
So it's the one that you constructed.
Yes, it's the green equation I constructed. Yeah.
It's not in the books. I mean, in the dynamical system book that we can find.
Actually, so the time dilation is something like in you can find in papers, but I don't know if there is any dynamical systems books that has it, right?
You have a paper about this time dilation.
Right.
And you started describing about this v1 equals this thing. So I mean, is it the way you approach to that equation, or was the thing that there is before and you took it? I mean, it's like a lemma or hypothesis. It's your own approach.
It's my own approach, right? So in the paper, basically we derive this method for chaotic systems, but I think it's much easier to introduce it in the context of periodic dynamics. Yeah. Okay. All right. So let's just demonstrate it for the Van der Pol oscillator. So let's actually again copy these. So again, this is the Van der Pol oscillator, and what we are going to be doing is that we are going to slightly change the parameter mu, right? And look at what is the resulting, how do we decompose the resulting linearized solution into a direction orthogonal and the direction tangential to the attractor. Let me see. I think I have written a code to print, to draw the tangent. So let me also copy this, and instead of drawing the tangent equation, over multiple trajectories, we're going to draw the tangent equation just right. Okay, so let's see. Okay, so we have seen that we have evolved the trajectory and the tangent equations as we are changing the first argument, right? So the first argument, which is mu, now has a tiny imaginary component. So we are perturbing that parameter in the imaginary direction. And then we are drawing what that tangent solution looks like. But now let me say V is equal to so V, because I have only one solution, right? Let me just take the 0. V is equal to that, and let me actually say U is equal to. Let me also take the because n equal to 1, right? I'm just going to take actually, let me just remove this n so that U dot imaginary component. So what I'm going to be drawing is I just remove the middle index so that it's going to be easier to draw. Okay, so make sure I still get the same thing. Yeah, I do. Okay, and this is going to be V 0, right? And V, so the imaginary part is actually V. Still got the same thing. Okay, now let's actually project the direction f of u out of V. So first of all, we need to compute the du dt of u dot real, right? So we want to compute the du dt direction. So f is equal to that, and we also want to reshape it into 2 and -1, which is the length of the trajectory. And then what we are going to be doing is v minus equal to, so we'll be multiplying v with f, and we're going to be summing over the states, which is 0, right? And we are going to be dividing this by f square dot sum 0, so that's the norm of f squared, now times f. Okay, now when we visualize du dt missing, oh yeah, I'm missing, okay, what I'm missing is time. It doesn't matter, I'll just give it as 0. Mu, which is where is mu? Okay, 1.0, and a is 1.0. All right, so this is basically the baseline parameters. And now what you see is the component of the tangent solution orthogonal. I need to actually make it axis scaled so that you are actually going to see the orthogonality, right? Because previously the axes are not scaled. Once I scale the axis, then what you see is that the tangent solutions are actually orthogonal to the trajectory, right? So this is basically our computation algorithm for the first component of the tangent solution that we know that is not going to grow in time. So to show that, let's say let's make two figures, and x0 dot axis scaled, x1 dot plot solution dot t, and let's say v. What happened? V dot transpose. I think I see. So I need to make this and ax0 dot plot. Oops. I think I intended to do 1 and 2. All right, so on the left-hand side, we should see the original plot. On the right-hand side, what we see is the time evolution of the two components of the first tangent solution, right? As you can see, as the trajectory comes onto the periodic limit cycle, the tangent solution now stabilizes. So for every period, the tangent solution also evolves periodically. All right. So that's good. Instead of growing linearly, now we have a tangent solution that never grows. It actually follows the primal solution to be a periodic solution. Okay, any question about this part? Okay, so basically for this component, because we have the tangent solution V1, right, analytically, so we can compute the resulting delta J1. Okay, and as remember, like previously, we cannot switch the derivative with the infinite time limit because the tangent solution grows to infinity. And now this solution to this tangent equation V1 does not grow to infinity, and as a result, we will be able to switch the limit and the derivative. So this is actually going to be equal to the limit of t goes to infinity, 1 over t, integration from 0 to t, right? Partial j partial u times v1, which is the derivative, which is the difference between the perturbed solution and the unperturbed solution over dt. Okay, what you can show is that as time goes to infinity, the convergence of the convergence of the finite time derivative, the convergence of the epsilon goes to 0, right? So the derivative is always represented as the difference between the perturbed solution and unperturbed solution divided by epsilon. So that divided by epsilon, as epsilon goes to 0, converges uniformly regardless of big T. And as a result of this uniform convergence, you can move that derivative operator out of the infinite time limit. And this is thus going to be correct. All right?
So one thing I didn't understand, why V1 doesn't grow in time. Is it because the life exponent is negative, or because we decompose it to V1 and V2?
it's because we decomposed it, and the only component that is going to be growing in time is along the direction that we projected out. Okay, so to mathematically prove it, you can always decompose the solution V into two components. One component, both components evolve according to one Lyapunov exponent, right? The first one is equal to 0, the second one is negative. Okay, and then you can show that once you project it out, the contribution from the first component is going to stay bounded, because that direction is actually, because the direction that's going to grow is exactly along the direction that you projected out. So basically, the contribution from that direction is going to be always the misalignment of the second equation, the second component, with the time evolution direction. So basically, supposedly the two Lyapunov vectors are actually already orthogonal to each other, right? So that the second Lyapunov vector is actually orthogonal to the time evolution direction. Then this V1 would actually be exactly the solution corresponding to the original tangent equation, but corresponding to the second Lyapunov vector. I mean, if they are not, then the second equation would actually contain a component that's associated with the second component along the time evolution direction, right? So, but anyway, so the solution to the V1 equation is only associated with is only a function of the second Lyapunov exponent, not the first one, right? So as a result, it stays bounded.
If it's chaotic, it doesn't remain.
Yes, if it's a chaotic system, then this V1 will not stay bounded. We actually have to project out not only the time evolution direction, which has a Lyapunov exponent of 0, but also all directions associated with a positive Lyapunov exponent. So we are going to pretty much be doing the same thing for chaotic systems, except for we are going to be projecting out not just the one component, but multiple components. And after we project out all the 0 and the positive Lyapunov components, we are going to see that the solution, again, like what we are seeing here, is going to be bounded. Yeah, good question. Okay, so again, let's just come back to the big picture. We have assumed the differentiability of J bar, and using the differentiability, decompose the delta F into two components, delta F1 and the delta F2. Up to now, we have already computed the effect of delta F1, right, which we denote as delta J1. Now, in order to compute the full delta J, we also need delta J2, which is the effect of the second component, the component of a time dilation, right? The component caused by an acceleration and deceleration of the evolution of the attractor. So that component, actually for periodic systems, is not so hard to compute, but you have to think with a different, from a different mindset, right? You have to think from the perspective of the density. Okay, so what does the density mean? So let's imagine I have a periodic cycle, and let me just take a segment of this limit cycle. Let me call it ds. All right, let me call the length of this segment as ds. What is the stationary measure of that segment of the trajectory? Well, the stationary measure is basically the fraction of time the limit cycle spends within that small section, right? It's basically, imagine the system goes over that trajectory, that part of the trajectory, with a small time dt. Then the density, or then the measure, right? The measure of that ds is equal to dt over the period. Agreed? Right? So for every period, the trajectory spans a dt within that small section. So if you take an infinitely long trajectory over many, many periods, it doesn't matter, right? Many periods versus one period, it doesn't really matter. The percentage of time you spend within that small component is equal to dt over big T. Okay, now my J bar is equal to integration over the whole, let me call the cycle to be lambda. So I'm going to be integrating over lambda a rho ds times j, right? So that is representing the J bar using ergodicity in terms of a spatial average and ensemble average, where the ensemble distributes according to this stationary distribution, which by itself is represented by the percentage of time you spend on that small component. Right? We have gone back and forth between an ensemble average, the density, and the time average multiple times. And we're going to be doing that a lot in dealing with ergodic systems. Right? Is it clear what we have done? Right? J bar, instead of using a time average, we represent it as an ensemble average. But the density over which we are ensembling, right, is actually distributed according to the fraction of time of a long time trajectory. Okay, so that can be represented as integration over gamma, right, a j u times dt over t. So what is dt? So actually, what is dt? If I'm given a small segment of the length ds, and if I know the speed over which I go through the segment, then what is the time I go through the segment? The length divided by the speed, right? Right, so dt is just equal to ds divided by the magnitude of du dt. Right? And the magnitude of du dt is, of course, just equal to the magnitude of the right-hand side, f. All right? Okay, so rho of ds can be just computed using ds divided by the magnitude of f divided by big T. Right? So that's my J bar. Any questions so far? Okay, so let's think about it a little bit more. So we are integrating, instead of over time, we're integrating over space, over trajectory, right? And of course, we are still averaging the objective function, but now there is a weight on this average. The weight is 1 over f. T doesn't really matter at this moment because it's a constant, right? You can move t out of the integral if you want. But then the real weight, the space, the location-dependent weight, is 1 over the magnitude of f. That means if f is large, right, you have a smaller weight locally. If f is small, you have a larger weight locally. This makes sense because if f is large, you are going through this part of the phase space quickly, right? Therefore, you are spending less time on it. So just imagine you have a time-lapse capture of the location on the attractor, right? So you take a snapshot every millisecond. When f is large, the points you are taking a snapshot of goes through really fast. So you are seeing a large space between adjacent snapshots. When f is small, the points you see are very dense because it goes through very slowly, right? So the density rho you can really just think of it as you're taking snapshots over a fixed time interval and how dense the snapshots are in the phase space. All right. So J bar can be represented as this kind of a weighted average over the trajectory. Okay. All right. So now with this formula, let's think about what is the impact of a small c, right? So now imagine we are looking at the second equation. We are looking at a perturbation from du dt equal to f of u perturbed into du dt equal to f of u times 1 plus c of u, right? So that's really our effect of delta f2, right? Delta f2 is this, right? Actually, delta f2 does not have the 1 plus, right? So it's f plus delta f2 has this 1 plus. So delta f2 is just fu times a c of u, right? So basically, this part is the delta f2 in the example. All right. Okay, and yeah, so this part is going to be the delta f2. Okay, so what is the effect of this? This has two effects. Effect 1, the magnitude of f is going to be changed into the magnitude of f plus times 1 plus c, right? Which is equal to the magnitude of f times 1 plus c, because c is a scalar. Okay. The second effect is t is going to change. The period is going to be changed by this acceleration or deceleration. So how is the period is going to change? So let's think about what is the period. The period is just an integration of this dt, right, over the entire trajectory. And dt is ds over f. So t is actually equal to the integration over the whole trajectory, ds over magnitude of f. It's going to be perturbed into a slightly different t, which is the integration over the same trajectory, right? So this is what's nice about decomposing into two parts, is that when you're looking at the time dilation component, you are integrating over the same, exactly the same trajectory, right? Because the f2 part, because the delta f2 part would not change where that limit cycle is. Over, again, f times 1 plus c. All right. Any questions on this? So basically, these are the only two effects. And let's look at how these two effects are going to change the J bar according to that formula. Okay, so J bar is going to be perturbed into, just to copy this, integration over the same gamma, the same Ju, right? Ju did not change. It's still the same function if you fix the location in the phase space. And then it's going to be ds over f 1 plus c and multiplied, let me actually move the t out of the integral, right? Then it's going to be divided by integration of gamma delta s over f 1 plus c. All right, so the original J bar before the perturbation is the same formula, except for whenever you see 1 plus c, you just get rid of this 1 plus c, right? So now let's see what is the effect of delta J bar 2. Let's actually, okay, so first of all, because C, we are thinking about C as an infinitesimal perturbation, right? So the effect on the numerator and the denominator can be added linearly, right? So so let me just illustrate why am I doing this. So let's say the numerator perturbed a little bit divided by a denominator perturbed a little bit can be minus a over b. When delta a and delta b are both very small, what is that? That is delta a over b, right? Basically, we are linearizing, we are differentiating this function. Subtracted by a over b squared times, oh sorry, this is delta b times delta b, right? So this is basically taking the derivative of this quotient with respect to the numerator and also take the derivative with respect to the denominator and add up their linear contributions, right? Okay, so delta J2 is the same. So basically, for example, if this is t, right, then delta J2 is, first of all, let me look at the effect of the numerator. It is going to be integration gamma j. The difference between, well, let me write ds over f. Then it's the difference between 1 over 1 plus c minus 1, right? So that's the numerator divided by t. Good? So that's the first component. All right. So let me if you're still confused, let me write down j, which is originally equal to ju ds over f divided by integration of ds over f, right? So basically what I'm doing is I'm fixing the numerator, which is t, and I'm fixing the denominator, which is t, and the numerator is this minus that, right? So that's the first component. Now the second component, I have to subtract, well, a over b is just j, right? So j times delta b over b. And delta b, so b is just a t, and the delta b is ds over f 1 over 1 plus c minus 1. And where, right, so this is basically delta t over t times j. Sorry, this is j bar, right? So j, this is j bar is equal to the long time average, right? So so basically what I'm doing is this is equal to delta a over b minus, there is a over b, which is j bar times delta b over b. All right? Questions? Okay, so what this is doing is that we are decomposing the effect of a small perturbation in the speed of the evolution into two parts. One part is a local effect, and one part is the global effect on the period. So if you look at this part, we see that if I have a local acceleration, so this is plus, if I have a local acceleration, then this part is going to be negative, right? If c is positive, then this part is going to be negative. I would be decreasing the weight locally on j. If c is, because I'm spending less time over the location. If C is a negative, I'm increasing the time I'm spending on the location. Therefore, 1 over 1 plus C is greater than 1, and this is going to be positive. I'm going to be weighing J more heavily at that location, right? But there is also a global effect, and the global effect is obvious if you consider C to be uniformly positive or uniformly negative. If C is uniformly positive, let's C is equal to the same constant and positive. That means no matter where I am, I'm going to be accelerating by the same proportion, right? And how does an acceleration or deceleration of the same percentage change the time average? For example, if I'm doubling the right-hand side, right? How does that affect time average? If I double the right-hand side with time average double, I'm going through the same trajectory, right? I'm going to be spending half amount of time on every location, but my period is also halved. It doesn't change exactly, right? Because the density is actually going to be exactly the same, and the trajectory is going to be exactly the same. So, therefore, if C is uniformly positive or negative, right, we are going to be computing as a first term something that's going to be uniformly positive or negative, and that needs to be compensated by the second term, right? So essentially, this is the local effect, and this is the global effect. This is the change again in the numerator of this averaging, and this is the change in the denominator.
I think as T, when we perturb, T also changes, right? So that's why we write the capital T or perturb as a function of density or size.
Yes, right. The capital T is a function of psi, but over here, whenever I'm writing a delta, right, then T, it doesn't really matter if I evaluate the T on the unperturbed or perturbed system, because I'm already having delta here, and a difference in this T would lead to a second order effect.
But this T is the one without any perturbation, the system without perturbation.
It doesn't matter if I mean, when I'm evaluating delta already, right, then it doesn't matter if I use the perturbed or unperturbed T. Like over here, it matters because before I take a delta, right, I need to know which am I. So yeah, am I using the perturbed or unperturbed, right? So, but when I'm taking delta, so in a Taylor series expansion, it doesn't matter if you use the derivative at the left-hand side or right-hand side if you are only keeping the first order term. Right, so basically in this formula, if you change this B to B plus delta B, it's still perfectly correct up to first order.
I mean, if the T changes, delta J bar also changes, right?
If T changes, delta J bar changes, but up to a very small number, right? So the effect of a change in T, so basically the change in T is proportional to the change in C.
Okay, it compensates. C compensates that changes. Right?
It's not really compensated. It's more like we are already taking a small difference, right? The change in T would lead to even a smaller difference. Right? Am I explaining myself clearly?
Yeah, I was confused because we just described T as a density, function of density. So, and for J2, we assume that it changes the period.
Yes.
So T changes. So T plus something, right?
Yeah, And this is the change in the period, right? This integral is actually the change in the period. Yeah, so this let me take the subscript also. Also, it's an integration along the trajectory, right? Okay, let's further simplify this. So 1 over 1 plus chi minus 1 is going to be equal to, when chi is a tiny number, it's just equal to minus chi, right? Okay, so basically delta J2 is going to be further going to be simplified as 1 over t times an integral of j times chi. Actually, we have a minus sign here. J times chi times ds over f, and the subtraction term becomes positive, plus now j bar times psi times ds over f. Right, and of course we can just combine these two terms, 1 over t and integral of j bar minus j of psi times ds over f. Okay, and now it's time to change back to time domain, because ds over f, right, is basically what is ds over f? ds over f is the amount of time we are spending, like, in this portion of the attractor. And the ds over f over big T, which is exactly what we have at the end of the derivation, ds over f over big T, is actually the density, right? So so that can be, let me I don't know, how do we make it a bit longer? Yeah, let me just write, continue to write over here, maybe using a better color. Yeah, you can see it, is equal to integration of j bar over j times c times rho of ds. So that's the density, right? Because rho of ds is equal to 1 over t times ds over f, right? Remember, ds over f is the amount of time we are spending on that part of the trajectory. So that's delta t. Delta t over t is the fraction of time we are spending over that trajectory, right? So that's integration over the phase space. And then we use ergodicity, right? Ergodicity tells us integral weighted by the ergodic measure is equal to a limit of t goes to infinity, 1 over t, okay, from 0 to t of, now we have the j bar minus j at ut, right, times c at ut times dt. All right, so that's what we get at the end. So that is basically the contribution from the time dilation term is equal to the product of is equal to the long time average of the product between two terms. One term is, are you accelerating or decelerating at that location? If c is positive, that means you're accelerating. If c is negative, it means you're decelerating over that location. The second term is the difference between the long time average and the local objective function. So let's combine them to think about if that makes sense. If at that part of the trajectory, the local objective function is less than the long time average, and I'm skipping that lower portion at a faster rate, that should actually give me a positive contribution to my long time average, right? I'm skipping a lower than average portion faster. On the other hand, if C is negative and J is greater than J bar, right? That would also increase my long time average because I'm staying at a higher than average J location for longer time, right? The opposite combination, skipping a higher than average faster, leads to a decrease in the time average, or staying at a lower than average location for longer would also lead to a decrease. Okay, make sense? Okay, so then this term we can basically this allows us to follow a trajectory, right? Or follow a trajectory over a period and compute these two numbers. This is easy, right? We can always compute the long time average, and we also have the local objective function at that time. And C, we have already said that over here that C is just equal to the time derivative of how much we project out, right? So once we already computed this projection out, and basically if we just take the time derivative and multiply with the difference between the time average, the objective function, and the local objective function, and averaging time, we should get the contribution from the second part. So we don't have time to actually code it up today, and Wednesday we'll code it up and look at the relative contribution to an objective function from this part we already have, and the second part, which is what we just derived. All right, so see you on Wednesday, and I'd be happy to answer any questions.